Hello everyone, my name is Lian Mendiha. In this video, I'm going to discuss my third machine problem using Vensim. First, let's read the problem I chose from Michael Heath's book, Scientific Computing, an Introductory Survey. The following system of ODEs, formulated by Lorentz, represents a crude model of atmospheric circulation. Taking sigma is equal to 10, b is equal to 8/3, r is equal to 28, and initial values y1 of 0 is equal to y3 of 0 is equal to 0, and y2 of 0 is equal to 1. Integrate this ODE from t is equal to 0 to t is equal to 100. Plot each of y1, y2, and y3 as a function of t, and also plot each of the trajectories y1 of t versus y2 of t, y1 of t versus y3 of t, and y2 of t versus y3 of t as a function of t, each on a separate plot. Try perturbing the initial values of a tiny amount and see how much difference this makes in the final value of y of 100. Lorentz is a meteorologist who has come up with a system of ODEs called Lorentz system. This is associated with the butterfly effect. This butterfly effect implies that in the absence of perfect knowledge of the initial conditions, our ability to predict its future course will always fail. The first differential equation indicates the rate of convection. The second equation is for horizontal temperature variation, and the third is for vertical temperature variation. I've already set up the ODEs in Vensim. Now, let me go through this model. For the first equation, for y1 of t, or the rate of convection, the inflow is y2 multiplied by sigma. The outflow is y1 multiplied by sigma. For the second equation, the inflow is y1 multiplied by r, while the outflow is y2 plus y1 times y3. This is plus because the equation for y2 is already set to inflow minus outflow. Hence, the minus part of the equation is factored out. For the third equation, the inflow is y1 times y2, and the outflow is y3 multiplied by b. Let us check the constants sigma, r, and b. Sigma is equal to 10. B is equal to 8/3. And r is 28. These sigma, r, and b are parameters proportional to Prandtl number, Rayleigh number, and certain physical dimensions of the layer itself. The initial values for y1, y2, and y3 are the following. For y1, the initial value is 0. For y2, the initial value is 1, and the initial value of y3 is 0. Before we integrate, let us first make sure we have incorporated the appropriate integral method and the lower and upper limits. The integral technique is Runge-Kutta. Runge-Kutta is the most appropriate for Lorentz system based on other modeling codes that I have researched. The lower limit, or the initial time, is 0, and the final time is 100. Time step is 0.03125, and this is preferable for stable results. Now that we've set up everything, let's run the simulation. The plots of the three equations can by dragging these three elements and clicking the graph button. You can zoom a part of the plot by dragging this here. The plot is from t is equal to 0 to t is equal to 100. The green is for the vertical temperature variation, blue is for the horizontal temperature variation, and red is for the rate of convection. The phase portraits can be constructed by customizing graphs. From the inputs, the phase portraits for y1 versus y2 looks like this for y2 and y3, and this is for y1 and y3. From these three plots, we can see a butterfly effect. For the last part of the problem, let's first determine the values of y100 before we perturb the initial values of y1 or y2 and or y3. We can see the values of y of 100 by clicking this table. Let us take note of this by taking a screenshot. Now let's perturb the initial value of y1 to 0.001. Let's run the simulation once again and check the values of y of 100. Tiny changes of the initial value of y1 made a significant difference of the values of y of 100, as we can see in this table. That is all for this video. Thank you.